Okay. So what we're going to do today is we're going to see how far we can get through chapter 6 with some new prologue predicates that are built in.
Did you update your slide?
Let's review the data objects in prologue. Do you remember this from chapter 2? This is a bit of a review. Okay, so remember, all data objects are either simple or they're structures. And then simple objects are either constants or variables. And then constants are either atoms or numbers. Now, do you remember what terms are in this picture? Do you remember what the terms are? Yeah, they are the leaves. Yeah, atoms. So here's what we said the terms are. Atoms, numbers, variables, and structures, these are all terms. So a little bit later in the lecture today, we'll have to remember that. So are we good? And now the first thing that we're going to do is we're going to show how these you can actually test. So here in our third slide, the type of a term can be tested by the following predicates. So we have 1, 2, 3, 4, 5, 6. We got 7 predicates here, right? And these predicates can test what these variables are, okay? And furthermore, the variable doesn't even need to be instantiated, and that's what the first one does. Look at what it says. Var capital X. Capital X is a non-instantiated variable. So let's demo that. Okay, so what did that slide say? Var, the var predicate, it said X, capital X is a what? What did it say? Non-instantiated variable. So can you predict this? Var lowercase a. Correct. How about var capital Z? Yes. Is everybody good? Now how about this? Capital Z match A, and now let's do var capital Z. Now can you predict this? No. And can we do this? How about this? Var capital Z, and then let's just change the order here, and then let's do Z match A. Now, how about this one? Now, what happens with fit? Oh, do you think it's going to be Z match A? It is. Okay, so let's go back to our slide. And take a look at the second one. So the second one says non-var, okay? And non-var X says what? X is not a variable. Okay, so let's predict some non-vars. So let's do non-var a, lowercase a, and what do we have here? Yes, excellent. And do non-var and then capital Z. And what do we have here? No. And let's do the same thing we did before. Let's do Z, capital Z match A and non-var Z. And what will that be? Z match A. Wait, was our prediction wrong there? So once we do Z match A, Z is an instantiated variable, right?
Isn't it still a variable? It's just instantiated.
Yeah, but non-var means X is a non-instantiated variable. Wait, is that right?
X is not a variable.
Sorry, it's X is not a variable.
So it can be an instantiated variable.
Right. Are we good? And then if we do now, but now let's switch this one around. Non-var Z and Z match A. Oops, match A. Okay. So, what is our conclusion? var capital X succeeds when non-var capital X fails and vice versa. Are we good about that? Is everybody cool? Now, I don't think I'm going to switch back to the slide, but do you remember what the next one was? It's atom. We'll take a look at the slide in a minute. But what do you suppose this is going to be? Of course, what this means is X is an atom, you know. So if we say atom ABC, now is that an atom? Remember our terms? Is this an atom?
Yes.
It is an atom, okay. How about atom 3.14? Okay, correct, it's no. Yes, we have no bananas. And what is atom, what about this? Atom, do you suppose this is an atom?
No.
Really? Because, I mean, you know, you can use that as a functor, just like any other, you know, like you can use it. Yeah? And how about this? Let's do one that has a little structure. P, A, B, C. What do you suppose about this? No. All right? Let's do integer. The next one was integer. So let's do integer 3. So what do we have here? And integer, how about 3.14? We'll just do these all, run through them all. What do you suppose here? No, because it's not an integer. Is everybody good? And suppose we do integer, just for completeness, ABC. And that's also no. How about float? These were all on the slide. How about float? Yeah, floating point is what that means. So this is obviously going to be what? Yes. And float. So without a decimal, no. And then float ABC, no. Are we good? Now, how about atomic? Maybe we should go to the slide for this. All right, so what we saw then is non-var, atom, X is an atom, integer X is an integer, float X is a real number. Now what about atomic? X is either a what? An atom or a number. So do you see there's a difference between atom and atomic? Is everybody good with that? All right. So let's try. Let's see if we can demo that. So let's do atomic 3.14. So what do you suppose this? Okay, correct. And atomic, and let's do atomic ABC. What do you think here? Yes, but now if we do atomic, because of the way I said it, you don't even have to understand it because you know this is going to be no, right? How about if you do atomic P, A, B, C? No. Are we good?
Could you do any of those things you did with Nova where you instantiate something?
Oh, good question. That would be a good demo. Let's try it. Let's do, which one of these succeeded? Atomic ABC. Let's do X. Let's do X match ABC. Now we know if we just do this that that's yes, right? So let's do X match ABC and let's do atomic X. Is that what you want? Does anybody want to hazard a guess here? We know the first goal is going to succeed, but what's going to happen here? This should be one that I have on my list of things to do. Do you want to make a guess? You think it succeeds? If we did atomic, wait a minute, should we do atomic, did we try atomic X? We didn't do atomic X, did we?
Atomic X should succeed because I think that's very consistent.
So now let's do, oh, I don't have that in my history anymore. So now let's do atomic, no, sorry. Now let's do X match ABC and do atomic, oops, atomic, pressed return by mistake. So anybody want to guess this? But let me see, X, yeah, X is not atomic, but yeah, so it uses its instantiated value. Yeah, that was a good, thanks for that demo. All right, now let's take a look at, so with that in mind, let's take a look at some programs. So let's do, we have this predicate called count, and let's see up here what the specification is. So we say count ALN. N is the number of occurrences of atom A in list L. Are you with me? So N is like our output parameter. So we have A is an atom and L is a list. So let's see if we can demo count. So let's do, before we look at the implementation. So let's do count A, and then suppose we have A, B, A, right? And then we'll have N be this N that we're looking for. And now, what should this be if our description here is correct? 3. Ooh. A, B, A, capital N? Oh, I did not consult yet. Sorry. What is this? ch6.pl, quote, boom, boom, boom. Now let's try that. Oops. No, we don't need to. Okay, so now, say what your prediction again? 3. Right, and are there any more solutions? No. Okay, so now let's do this. Let's do count, instead of doing A, oh, actually before we do this, let's see if we can understand the implementation here. So does everybody agree that this is a good base case? It doesn't matter what the atom is. If the list is empty, the count has to be 0. Are you with me? But then what? If the list is not empty, then it has a what? It has a first and a what? And a rest. Are you with me? So if this matches this, which they are if we use the same letter here, then we have succeeded, right? And so now what do? We do a cut right off the bat. Yeah? And then we do a count of this one with the rest, and we put that in, we assume that N1 will have the result of that, and then we compute N to be N1 plus 1. Now, is everybody fine with that? Now, if this one doesn't match this, then this one will, this will fail, and we will never get to the cut. So therefore, we can backtrack. Now, is everybody clear on that? Is everybody with me on that? If this one is not the same as, if this one and this one are not the same, they won't match, and so therefore we won't get to the cut, and we'll just fail right on here, and we'll go to here, right? On the other hand, if these first ones are the same, then we'll come to here, and we'll do this, which will start all over from the beginning. All right? And so on and so on. And then, so if these don't match, the count with N is the count of A with just the rest and N. Yeah? So, but now, check this out. Let's do count. Let's change our demo here. Let's do count A, B. Now, before we did count A, B, A, and N. Now, let's do count A, B, capital X, capital Y, and then we're going to put this in a new variable. Let's call it NA. Are you with me? Now, what do you suppose is going to happen here? Any predictions? Will it be an instantiation error? Go up to this code and see, will it? What do you think? Yeah, you're thinking X and Y will match to A, and then will the count still be 3? Will it,
Different possibilities, like do 1 with neither of them match to A, and
well, I mean, I think we should be able to predict this, shouldn't we? We know, because what's going to happen here? The very first time isn't the very first time we do it, it's going to be like this. Now, will it match here? I mean, because this will be A, and then the L will be what? The list BXY, right? And then it will recursively do the same thing, and then the L will be XY. But now when the L is XY, then what will happen? Yeah, so I think you're right. X and Y will match A, and the count will be 3. And are there any more solutions? No. Are you with me? But now here's what's happening. Here, how about this, though? If we do the same thing, only if we call this NB, and we put the B here, right? So here, first we counted the number of A's. Now we're going to count. So now what is this going to be? Yeah, so wait a minute. How can you have 3 A's and 3 B's? Are you with me? In fact, let's try this. Let's try this. Let's do L match, and let's do, to match our list, A, B, X, capital Y, right? And then let's do count. Now see if you can predict this. A and big L and NA, and then let's count the number of B's in L and do NB. Okay, you guys, what do you think? The first one's going to be 3 A's and X and Y is instantiated to A, and the number of B's will be what? 1. Nice job. Are we good? Does everybody see how that works?
If
So-
you put something like, if you said A, B, X, Y, count C, next L, it would still give you 2 C's, wouldn't it?
Yeah. Oh, yeah. It would. It would. That was a good. That was a nice one. Suppose we do count. Suppose we do count C, and we do N C. Then what is this? 2. Yeah. So how can we solve this problem of having it just count the number of? So how can we solve this problem? So here's what we need: is we need count 2. That's going to be our count 2. Second version in case L has variables. So now how can we use those predicates that we did before? So that it only counts the 1A. What were those ones that we had? Okay, what were those predicates? Come on, you guys. I know it's Friday. All right. So count 2, same base case, right? Okay, but now what? So now it's going to be count. Now we'll do count AB, right? Instead of AA, because if it's AA, if it's one of them is an uninstantiated variable, then it'll match. So now what do we check? So now that we have AB, how do we check? Well, we check to see if B is an atom. Are you with me? So if B is not an atom, what will happen here? Like if it was the capital, if it was, what were the letters? Capitals X. So if B was a capital X, it wouldn't be an atom, right? So then this would fail and we would go on to the next rule. So now we check atom B. If that succeeds, then we match A match B, and then we cut. Are you with me? Is everybody good? Otherwise, no, oh sorry, not otherwise. And we do And then we do count 2 AL with the rest with N1, and you know what's going to happen next. N is N1 plus 1. And now we're going to do this with one clause. Or what? So, or what happens here? I mean, the only way you can get to that is if this doesn't work. So if that doesn't work, what do we do? Count 2 ALN. Yeah? Okay, so let's check this out. Oh, I forgot to finish this one up. And let's do, now let's do that one that we did before. Let's do, only this time we'll do them with count 2. So this is being count 2, and this will be count 2. And now with our new improved version of count, what happens? There's only one A and only one B, and those variables didn't get counted. Are we good? Okay, and then there's no more solutions. All right, now, so there are some predicates, and those are in your little toolbox of built-in predicates you can use. Now here's some more built-in predicates. We're actually only going to do the first 3 of these today. And what we have here is a way to construct or to decompose terms. All right. Do you remember in the functional paradigm that we said that you could actually write the read eval print loop in scheme, for scheme, in scheme? Do you remember how it has this self, ability to analyze itself and do its own thing completely? You could actually bootstrap up a system that was all written in scheme that would interpret scheme. And that's why was that? That was because the basic data type in scheme is the what? Is the list processing, and you interpret the first one as the function, the name of the function, or it didn't even have to be the name of it. It is the function, and then you evaluate the arguments and you apply the function to it, and you do all that recursively. And all those cars and cooters could be used on scheme programs. Well, what's the basic data type here in Prolog? It's not actually the list, it's the what? It's it has the shape of a predicate, right? And it's a functor and then a what? A parentheses and then a list of arguments separated by commas and then the close parentheses, right? That's what that is its basic. So in the same way that in the functional paradigm, that we have car and cooter to take apart the first of a list and the rest of a list so that we can actually construct construct functions that we can then return. It's the same thing. Prolog, it's the same idea. Prolog has the same set of tools to do that, but instead of being cars and cooters, what is it? It's functors and argument lists. Are you with me? Does everybody see the idea there? It's really all of these, hey, where's my little, didn't I use my laser pointer? Well, I'll just point. Okay, so take a look at, well, I want to point with my laser pointer. Did I not take it out of my bag? I did. Oh. Oh, here it is. It was under this little piece of paper. Sorry. All right, sorry for that distraction. Okay, so does everybody see on this first line right here? The thing that's built in on this first one is this equals ... All right? It's equals ... And this is pronounced univ. All right? And what the purpose of this univ is to take a term, and when you do univ, what you get is a list whose first is the functor and whose rest is an argument list. Are you with me? I'll do some demos right now and you'll see. You got a question?
Yeah. Would you put the argument list in brackets and put the variable?
Yes.
Okay, so that's two separate brackets.
Yeah. Yes. Now let me show you. So it's pronounced Univ, okay? And so check this out. Let's go back to our demo here. So here we go. This is the built-in Univ operator, and it's equals ... And the way, like what we had up on the slide, it's term Univ list, first is functor, rest is argument list. And so list functor and then argument list is a list that contains the principal functor of term followed by its arguments. Okay? So now, so let's do a bunch of demos here, and I think you'll see how this works. So if we do F, comma, and then we do A, B, C, like this, and then if we univ that with L. Now, based on that definition, what do you think is going to, of course on the left we don't have any variables, right? On the right we have a variable L, which is a list. So what will L be instantiated to, do you suppose?
The list, F, A, B, C.
Exactly. Now, is everybody, the list F, A, B, C, the functor and then the arguments. Is everybody good? Okay. So let's do, so now what happens if we do this, and instead of having L over here, suppose we say left paren, and then we say capital F functor, and then we do arguments. See, because suppose we want to extract the functor or we want to extract the arguments. Now what do you suppose is going to get instantiated? Yes, functor is instantiated F, and arguments are list ABC. Are we good? Okay. And furthermore, you guys, what's going to happen if we do this? Obviously, capital T univ, and then we do this, and we do F, and then we do the list A, B, C. So this is what you were saying, Shane, before the list. Are you with me? So now, obviously, what's this going to be? What's T going to be instantiated to? Is ABC, yeah. So you see the same operator. Isn't it neat how in Prolog you can do it on either way? It's not that, on either side of the univ operator. You see, you don't need it. And look, in the functional paradigm, we had, let's contrast this. In the functional paradigm, we had car and coulter to go one way. But how did we go the other way? Car was the what of the list? The first of the list. And coulter was the what? Was the rest. So given a list, we could extract the car and the coulter. But then, how did we put them together? We had what? Cons was what we needed, a cons to do the opposite of car and coulter. But do we need another univ? No. Because this is a declarative paradigm. Are you with me? So is that a, you see the contrast there? It just works on both sides with this, unification. That paper that I'm asking you to read, that unification paper talks about this, and it works on both sides. See, the matching works on both sides. How about this? How about if we do U, and then we do univ, and then we do capital L? Anybody want to predict this? U is a what? Yeah, so what do you suppose is going to happen here? Does that have the right kind of shape? Oh. How does it, why is that?
That just mean that it doesn't have any argument?
Is that, yes, that is the functor place. You're right. So if, in fact, to see that, we can do this. We can say U, and instead of doing L, we can do this again. And now what do you suppose, so now given that, what do you suppose this will be? The arguments will be empty and the functor is U. Is everybody good? And how about if we do, how about if we do 17 and then L? Do you suppose this will succeed? You might think it wouldn't succeed. It's a little bit surprising. Yeah. How about this? This is definitely, do you see a definite problem here? They're both variables and neither one of them has been instantiated, so there's no way it can do any kind of a structural analysis of it. So there's an instantiation error. And notice right over here that this is a two-ary, predicate. Okay, but we use it, it's used infix, it's used as an infix. All right? But how would we do this? If we said T match U and then do T univ L, now what's going to happen? It's going to be like we would expect. We did with just U. Are we good? Is everybody good? Okay, so now let's see how we can use univ. Check this out. Now this is a really interesting example. This is a really good example of how to use univ. Our author, I really like this book. Bratko has done a really good job here with examples of how to use these features. So look at this. What we have here is square. And a square has one side, and a triangle has three sides, and a circle has a radius. Now these are all just comments, right? So none of this is in the database. These are just comments. So, but given that a square has a side, and a triangle has three sides, and a circle has a radius, what we want to do is we want to enlarge. We want to enlarge a geometric object, okay? And so what we are going to do is we're going to implement this predicate enlarge, and it's three-ary. So it's fig, factor, and fig1. So fig is a figure, which will either be a square or a triangle or a circle, and factor is going to be the factor by which we enlarge it, and fig1 is going to be the resulting figure. Do you see what I mean? Now, do you guys remember, we actually did this exact same thing in our data structures when we introduced object, when we did our very first object-oriented project, which was the, remember the square and the right triangle? And I think you guys actually did scale. Didn't you do scale? This is scale. This is how to do scale in Prolog. All right? So check it out. So fig1 is fig with each argument multiplied by factor. Now we are going to assume that the arguments are already numbers. Okay, so this doesn't work if the side or side 1 or side 2 or radius, if they're uninstantiated variables, it doesn't work. So we are assuming that they are going to be already numbers. Now, so that I don't have to keep typing all this stuff, and when you can use this feature. What I did is I put the queries here so I wouldn't have to retype them. So now look. So look at what this is saying. This is saying enlarge square 5 by 2 giving figure. So what should figure be instantiated to? Square 10. Yes. Does everybody see how that works? Okay. And let's do another one. If we enlarge, on the other hand, if we enlarge a triangle, so let's copy this, paste here. If we enlarge a triangle that has 3, 4, 5, and we enlarge it by a factor of 3, what should it be? Figure should be what? 9, 12, 15. Yeah? And is there another one? I'm not sure. Well, there's not, but you can see that a circle radius, blah, blah, blah. And obviously what we have to do is we have to do it for any functor with any number of parameters multiplied by that scale. So how in the heck are we going to do that? How in the heck are we going to do that? Well, let's think about it. First of all, the very first thing that we're going to have to do is peel off the what? Because what is the figure, here, what is this figure? What do we have to have access to? The what? The functor, and then the what? Yes, a list of arguments. So we're going to have to do some list processing here, right? But the very first thing is to peel it apart. So look, so we do fig, univ, and then we have type and parameters. So what is type going to be instantiated to when we did this first one here? Type was instantiated to what? Square, and then parameters was instantiated to, parameters was instantiated to 2. Here, type was instantiated to triangle, parameters was instantiated to the list 3, 4, 5. Are you with me? So then after we do that, now what do we do with parameters? Now what do we have to do with parameters? Yeah. So we're going to have another predicate that we will define later called multiply list. And how are we going to design multiply list? Well, we'll assume that parameters, the first one is instantiated. Are you with me? We will assume that capital F is a what? Is the factor. And then parameters 1 should be the what? Should be the list with all the parameters multiplied. And then, if that gets instantiated correctly, how do we put them back? Yeah, fig 1 univ, type parameters 1. Are we good? So now all we have to do is what? Do multiply list. Well, what's the base case for multiply list? The empty list, right? Okay. Well, yeah, the empty list with any factor, doesn't matter what the factor is, the resulting list is empty. Okay. Otherwise, but if the list isn't empty, how do we extract the first one and do the operations on it? So now what's the next one going to be? Are we good prolog specifiers now? Tell me what's on the next line. Multiply list, and then what?
Something like first bar rest.
Yeah, first bar rest. Okay, so we'll call it, our author calls it X bar L. Okay, and then F, okay, which this F is going to match with this F up here. And then this parameters 1 matches it. So now if what? Is, yeah, we use is. Excellent. X1 is what? F times X. And then what? Multiply list L, F, L1. Are we good? Does everybody see how that worked? Excellent. Okay, good deal. See you next time.